So we have the pleasure of hosting this week. So we got Ashish Sharma down here with us in Baltimore at Johns Hopkins. So Ashish is on faculty at the University of Illinois, of course, in the Department of Atmospheric Sciences. And he also sits in Chicago, where he is the director, or the urban, not the director, the climate and urban sustainability lead, right? The climate and urban sustainability lead at the Discovery Partners Institute, which works across all campuses in the University of Illinois system. And so Ashish has a ton of interesting work that he's going to share with us today on urban climate and other topics, really around the world, but very importantly to us, associated with the Baltimore Social Environmental Collaborative. Ashish is a key player in Crocus, which is, of course, the Chicago Urban IFL, and in a number of other research initiatives that he leads and participates in on urban climate in Chicago and elsewhere. So Ashish's training at both his master's and PhD came in aerospace engineering from Arizona State University. He also holds a bachelor's degree in electronics and communication engineering from JP University of Information Technology. And before going up to Chicago for his current position, Ashish was working in Urbana-Champaign, where he was doing state climatology work through the University of Illinois system. And so he's got a varied background and a number of fascinating projects to talk about today. So Ashish, over to you.
Thank you, Ben, and thank you, Dan, for inviting and the colleagues at Penn State. So I'm going to go through a lot of slides with a lot of animations and pictures and read through a lot of things. And if you have questions, feel free to stop me in between, or we could take the questions at the end. And let me know when to stop, maybe. Okay. So I represent here University of Illinois System, and we'd like to give you a little bit overview of what we do there. So at the University of Illinois, we have created a Discovery Partners Institute to grow tech economy. Our goal is how do we commercialize and work with industry primarily, and our goal is to have an annual impact of around $2.8 billion. At the University of Illinois system, we have around $19 billion impact that we put on the state. So we really want to propel that. And this is our new upcoming building, which the Illinois governor really gave us around $500 million to produce. And this is right next to the Chicago River. So right in the downtown. It's the 78th neighborhood, which we'll start breaking the ground sometime this summer or fall. We work at the intersection between industry and university. How can we really use the expertise that the university system has, all three campuses and our partners, to really work with the industry. We work on a lot of cross-cutting areas related to food and agriculture, finance, insurance, information technology, infrastructure, and many other areas. And I lead the climate program at the system. These are a few of the partners. We are growing as we speak. I think these are slides maybe a year old. It shows around 20 partners that we have, research partners across the world, of course, regionally, which are all three University of Illinois universities, Argonne, Chicago, and Northwestern, and Fermilab, and also a lot of partners in UK, Israel, and Southeast Asia, Brazil, and Mexico. We rely on external fundings. State of Illinois supports us. We really also have international projects like PIRE and global centers. So let's get back to the talk on climate science to actionable urban solutions. Today is Earth Day. So I'd like to share an elementary school kid's perspective on climate change. This is my daughter, Ishika. Oh, okay. And she loves to be outdoors and play in natural environments. And she she asked me for a paper. I posted this 1 year back on LinkedIn. Can I have a paper? Like, what do you want? I took out from a printer and gave it to her, and she drew this drawing where on one side she's showing that very reasonable temperatures with nice trees, with having flowers and fruits, while on the other side she put together buildings with a lot of emissions and some contrasting colors showing heat and all. Wow. So I think as we faculty and researchers speak and have these Zoom sessions and working from home, our kids are also learning implicitly about climate change. Okay, so lessons from a collective wisdom. Back in 2022, IPCC released a report on impacts, adaptation, vulnerability, really talking about how are we perceiving impacts globally. And right now they started commissioning a new report that will look around cities too. So cities, from that report, cities are under increasing stress related to food, energy, water, and insecurities. If you think about adaptation targets, they're hitting a lot of soft and hard limits. There is always a debate between mitigation and adaptation, how much mitigation we should do and how much adaptation, what should be the balance between these two. And in general, we at departments really work in siloed approaches. We need integrated solutions. We also need to think about how do we include liberal arts and humanities kind of disciplines as we think about it. History is written by historians, right? And they should be part of this conversations around climate change, right? How do we at the same time use historical indigenous learnings and nature-based solutions as well? So overall, the window of opportunity is closing rapidly. We need all hands on deck to really address climate change issues. And likewise, UE has put a lot of money in looking at climate change in cities and change the landscape and how funding agencies are looking at these issues too. So what do we need to make our cities resilient? Okay, so we need crisis, knowledge, technology, partnerships, vision, and leadership. And unfortunately, we have gone through all of that. We had COVID, right? We now learned how to work in a crisis situation. Technology is advancing each day, and we have knowledge. We are learning to build partnerships in our ongoing projects. For example, we have vision and leadership from the universities as well as from agencies as well. So if you think about cities, and today I'm going to talk a lot about cities, how cities are taking up charge and what we are doing in the cities domain. You think with what has happened geopolitically over the last decade, cities have become leaders, right? A lot of city organizations, they are ready to lead, encourage, and enact solutions. I'll share more examples of that. And they do because climate change is a threat multiplier for them. Around 50% of populations lives in cities, and many more will live in the future. And they can do it, and they can make change really faster than if you think of global or national level scales. As a pathway, we also collaborated with the Chicago region, which accounts for 275 municipalities in the Chicago area, including the city of Chicago, to really come up with a climate action plan. And this is one of the few examples where cities and regions have really collaborated with universities to come up with a very comprehensive action plans, and true example of academic, industry, and municipal and nonprofit partnerships. I'll also talk a little bit about what we do. I lead the DPI climate ecosystems back in Chicago, and we do fundamental applied and translational research. Okay, this is our tree, our climate ecosystem tree, where we have really strong knowledge and experience working in climate research, right? How do we do fundamental science? But we are making sure our roots and stem is strong, and then we start diversifying into applied research, policy, environmental justice, industry, and education. I'll not go through the examples, but all the examples, but you can go to our website and get a sneak peek of the projects that we work on. Coming back to urban science and urban research, if you think of how you should work on it, as a climate scientist, we really a lot of times work in this middle box where we look at urban resolving models across scales. But it's really important to understand what are the urban drivers, and drivers could range from global to local scales, which could be related to economic development, how population changes are happening in migration, out migration, governance and equity lens, and technologies that are emerging, and technologies at times are very disruptive. So how do we account for those things as we think about drivers within the urban systems? Then we look at urban resolving models and scales, where we try to look at a lot of science questions that we are interested in, really driven from the needs, then impacts and risks and outcomes and solutions. And read more about this in this comment article that we wrote in Earth's Future. So if you think about that second box where we primarily work in, we really work to bridge urban scales. We do multi-scale modeling from global to regional to local and hyperlocal scales. Study processes like heat islands, lake breezes, heat waves, and air quality impacts. We do numerical modeling where we do data simulation, looking at subject variability, aspects related to meteorology, hydrometeorology too, flooding as well, and air quality. How can we do adaptation and mitigation, where we are looking at rooftop solutions, energy consumptions, vulnerability, nature-based solutions, and so on. We also work on climate action plans that I showed briefly, in the previous slides, policies and transdisciplinary research. We have started looking at new areas of research where how climate intersects with crime, right? And also going into machine learning domain too. Now I'm going to give you a bird's eye view of what happens during the daytime at the urban-rural interface. So when the sun rises, you see the cloud cover increases because of the solar radiations. Some of the radiations are trapped, and some get reflected back. The trapped radiation really start causing heat over the land. That's the greenhouse gas effect, and long wave radiation is trapped. And the maximum temperature over rural areas starts increasing slowly. While urban areas, the radiation gets trapped within the urban canyons. At times, there might be high albedo, which we are trying to have in urban communities. Generally, it is not there. But how can other urban factors like roads and transportation and houses and others really contribute to these dynamics? There are impacts related to irrigation that might create oasis effect, or impervious areas also might create a drying effects. And then transportation creates around 25% of emissions in the urban areas. On the top, we have entrainment, and overall the maximum temperature in our over urban areas is higher or same in comparison to rural areas. It might change, but in general, if you look at it, they might it's comparable during the daytime. While during the nighttime, again, because of the cloud cover and greenhouse gases, outgoing radiations are trapped over rural areas, and the minimum temperature increases faster than the maximum temperature. Okay. We were talking in the morning about the diurnal temperature in concepts. So we are looking at the minimum and the maximum temperatures here. While over the urban areas, the building starts radiating heat that they have stored, they have captured during the daytime, and there are flows and there is entrainment happening over within the boundary layer, trying to have some mixing. And if you look at the overall statistics, there's a significant increase in T minimum compared to rural areas, because a lot of radiations coming out, heat coming out from the built environment, and that leads to reductions in diurnal temperature range. Okay, and the concepts of urban heat island are usually the nighttime concepts, which gets amplified during the night. Of course, we might get high temperatures during the daytime as well. So overall, if you look at urban systems, we face flooding, heat, marginalization, stress, flood, extremes, tornadoes, gentrifications, jobs, green spaces, and many other things like that. So these are the problems created by us, and we have to find solutions, right? So this is just an infrared movie which is showing Chicago downtown, and one of my colleagues walking through here. As you can see, humans, we are part of the ecosystem, are also part of the problem as well as part of the solutions, because we also contribute to heating, even though the magnitude might be less. But the impact pathways, how we create urban stress, is a lot more. Okay. So if you look at the current urban environment, this is a depiction of Chicago area. We have the Lake Michigan, built environment, emissions, and natural areas. We have high urban heat, high energy stress, and that results into public health outcomes, poor public health outcomes, and crime, and unhappy community of people, especially the marginalized and non-justice community. And that leads to higher crime rates as well. Our urban utopia is to have resilient urban communities with adaptive choices. How can we have much more solutions, adaptive solutions, or mitigation strategies like green roofs, school roofs, more vegetation within the urban canyon and within the cities, so that we can have low energy stress as well as improved air quality, low heating, and so on. Of course, if we try to have that, whatever the local scale dynamics are with respect to, say, lake breeze and other things will also get impacted. So it's not that if you take, say, for example, vitamins, and if you eat a lot of vitamins, it's good for you. Okay? So you need to really identify what are the optimum solutions that you can come up with. So that's the space we are working in to really create optimum solutions. Overall, given all the background that I have shared, urban systems are multi-scale, interdependent, social, natural, and engineered complex systems. Very complicated. They have around 2-3% of global landscape, but creates havoc around the world with the things that we do there. Okay, and this is a simulation with a 1 kilometer data sets over Chicago for temperature within the boundary layer. And you might see this is a cool simulation and cool results, but if you think from a community's perspective, this is useless, right? They're not getting any useful information from this. So how can we really work at scales where really we can help communities make improved decisions? That's where that's the area we want to play in. So we want to improve from a scientific lens. We really want to improve the urban boundary layer processes, and we want to create fundamental and translational science so that we can do the science to serve the society. So that can be done in two ways. First is bridging the urban scale gaps, and this is one of the classical figures that I'm going to show. So you can work on city scales. The questions that you aspire to answer depends on what you're trying to address, right? And then you design those experiments based on those scales. So if you're looking at large scale features, how cities impact, you would like to do work on city scales. Likewise, if you want to go into the neighborhood scales, the questions might be different. And if you're looking at micro scales, questions are different. And eventually, if you're looking at individual scale, the models and the questions would be different. So there's no right and wrong answer that we should work always at hyperlocal scales. Not necessarily, it depends on what you're trying to ask. So based on the questions, we need to design, based on the need, we need to design the questions. And when we do that, we need really tools which are really relevant for different sizes of cities and different problems that we are trying to solve. So that's why I said we need complicated models as well, and we need very simple models to answer questions. This is spatial scales. When we look at the vertical scales of interactions, we are really looking at atmospheric, land surface, and subsurface. So how do we look at this integration in the vertical sense as well as in the previous slide I was talking about horizontal? So we are working in this domain as well. How do we couple atmospheric and land? There's a lot of work going on, but also we are looking at subsurface and land surface through biogeochemistry processes. For example, a lot of work is being done in Crocus as well. So if we look at computer models, climate models, or whatever you call them, we work at different scales. These are regional scales, city scales, and neighborhood scales, right? And neighborhood scales, these are different examples. As we go down to different scales, the way we show the information also changes. Here we are showing at a grid resolution, and here we are showing at the census tract, because that's the city really, it makes some sense to them. And then when we go to the neighborhood scales, we really show explicit presentations of buildings and trees and other things. These concepts are really important because urban areas are so complex, right? If you look at urban heterogeneity, see what all is, this might be within a 1 kilometer domain. This is downtown. You have tall skyscrapers, smaller buildings, cars, parks, golf courses, and everything else, right? How does it all account if you really want to understand? There are processes that are, if we are working on regional scale, this might be just one grid box and there's so much going on. How do you account for that? So that's the important question. So how do you account for these heterogeneities and the impact pathways that the surface has on the boundary layer to account them? People talk about urban heat island. We are really interested in talking about heat isolates. There are heat pockets within the urban areas which are hotter and some are cooler and so on. How do we start talking about those? Of course, if you average them out, it would be hotter in comparison to the rural areas, but everything is not always hot, right? How do we address these issues, and target mitigation strategies for these areas? So this is where we are focusing on. At the same time, if you look at regional scales, these are the Great Lakes kind of a cross section. We are really interested in large scale flows, for example, our jet streams. How do they, what are the impact pathways in which they touch Chicago region and create temperature swings or precipitations? At the same time, evaporation from the lakes that creates lake effect snow, especially during the winter times. While during the summer, we have the long transport from Gulf and Atlantic that brings moisture, as well as extreme summer storms, which are happening due to the localized convection happening over the lakes and over the land. And then this heat wave impact, which are regional, as well as the extended impacts over far off Midwestern areas, creating droughts or floods. So this is just a schematic where we are trying to understand urban heat island and heat wave interactions. How do we understand those couplings between the localized phenomena and large scale phenomena? So I just tried to open up the landscape to talk about a lot of problems and complexities at different scales that we have. Now let's talk about solutions. So I gave you a lens to solutions previously as well, but this is more sciencey diagram where we are talking about different types of solutions, green roofs, white roofs, works on different principles and mitigation strategies to reduce heat and make changes in the boundary layer. And these are very common solutions, which are, say, green roofs, which you can use green roofs. You can use forests, permeable pavements, photovoltaic roofs, electric cars, cool rooftops. Few technological, engineered, and ecological mix of solutions. So how do we look at these solutions individually? I'll give you a few examples of that in a while. Before going, I would like to also talk about when we create these solutions should benefit the larger ecosystem. Of course, the solutions will, if you plant a tree here, right, it will have the neighborhood and that person who's the tree is next to. But how can we think of these solutions helping the larger ecosystem? Okay, so that's a bigger question we should think about. How can we invest in cleaner energy sources? Nature-based solutions. How do we decarbonize transportation and promote public transportation as well? How do we enforce regulations and emissions from industries and vehicles? Nature-based solutions, I said it in the top as well, related to heat, air quality, and flooding. Improve urban planning, urban design, and so on. So we need to be very cognizant that only one thing can't help. We need a mix of everything, and so we need to make a soup where a lot of investments needs to be diversified the way we do it in our stock market, right? Our own as well. We don't put everything in only one stock. So how do we work on that? That's why what we say is we don't work on urban climate, we work on urban science. So because science is incorporating a lot of input and a lot of lens to it. So let's look at a few of these solutions. This is photovoltaic panels, for example, using over rooftops. I'll not go in the math. Simple photovoltaics works on the principle of reflection of radiation. So how sensible heat is reflected back. But we did these simulations to look at the photovoltaic production potential, and these are the early results. So don't quote me on the values yet, but we are working to use measurements to validate and then publish. And then how do we make sure what is the air conditioning consumptions if we use photovoltaics over the whole region? So if you look at these results, in some ways you would say this is not useful because you are putting photovoltaics over the whole region. But if you compare these kind of results with a very localized observation that you have, you can see some comparative results, and I'll show you in the next few slides. We also tailor these kind of results to really communicate. I think communication is the key when you're working with the communities. What is the potential of of installing these on CO2 offsets, right? These are the simple mathematical equations that you can use, scaling factors to really convert the same information, or how many cars off the road can you take in a day? So saying the same information with communities and with the stakeholders and policymakers to really make them understand the advantages of these kind of solutions. Likewise, with green and cool roofs, again, this is a mathematical representation of how green roofs and cool roof works. Green roofs works on the principle of transfer of sensible heat to latent heat, and cool roofs works on how higher albedo over the rooftops is converting the sensible heat into shortwave radiations and reflecting it back. So here we are showing a diurnal temperature profile of roof surface temperatures with green roofs and showing how much is the maximum potentials of reductions in temperatures. While we do that, what we also found is within the boundary layer height up to 3 kilometers, the temperatures also decrease during the daytime. There's a reduction in temperatures happening. So it's not only decreasing temperatures at the surface, but it is also decreasing within the boundary layer height, which might sound like a really good thing, right? We're reducing the temperatures everywhere. So the question comes down is, if you're using these solutions, are the transport mechanisms or the photochemical processes that happen within the urban area, which are important? So to address that, we took a cross-section A to B, as shown on the top, and then plotted the vertical velocity and the boundary layer height. And what you could see, if we go from A to B, the bottom part of A2 going from A is the rural area, and the top part is the urban area. If you don't do anything, it's a conventional rooftop, you can see the boundary layer height is up over urban areas is up to 2.5 kilometers. But when you start using aggressive mitigation, then the boundary layer drops to 2 kilometers. So the question becomes, and also you see this vertical updraft, those are the colors. So the vertical draft intensity is also lower, and those are the bigger updrafts. You can think in terms of signal to noise ratio comparisons, for example. So what's the message from this? What I learned from this is, if you take a water in a pan and put it on a high flame, you will see a lot of convection happening. It's getting more heated up. And if you put some pollutants in it, you can see a lot of pollutants going up because it's rising. So if you make the urban environment really hot and do whatever you want to do in the urban environment, you can make sure the pollutants are going up, right? This is a good thing. But if you're putting a lot of mitigation strategies, you are reducing the convection of the pollutants up, right? Think with that analogy, but we are really situated next to the Lake Michigan. What Lake Michigan does is it also advects because of the lake breeze. So you have pollutants coming up, and it might help advect, or whatever large scale flow might help advect. But if you aggressively implement green roofs as an example for illustration, you are allowing the pollutants to not go that higher by convection. At the same time, you are decreasing the lake breeze intensity because you have changed the pressure gradient from lake to the land. Now land is not that hot. Let's say lake is at the same temperature. The temperature difference is going to change the pressure gradient. Now the intensity will be less. So you have not lifted much and you have not affected much. So it's the same example. Too much vitamins are bad as well. Okay.
So you posed this, but is this 100% penetration of green roofs, or what's the?
Yeah, this is the maximum. So we want to create bounds, right, in which we want to play. So this is just an example that if you aggressively use this without thinking in the right direction, then this might lead to a problem. We ran a chemistry model coupled with chemistry, and our hypothesis is validated with this, but we have not published because we have not measured. So we are looking for measurements to put in this round of within the crocus to really come up with to validate this and maybe hopefully publish it. We'll redo the simulations whenever we do that. So what message that it give to us is, of course, these solutions are good, but we need to really find targeted locations where we implement so that we can have these convective rolls that you're seeing. They are well mixed in the atmosphere. You have a lot of convection happening here. Here it's not happening. Other places it's happening. So the mixing in the atmosphere is there. Okay. Another example is using urban vegetation. We all talk about urban heat island, right? But we are also talking about CO2 dome. So how and we talk about trees with respect to reducing heat as a matrix. They also help absorb carbon dioxide and carbon emissions. So we are working on the land and subsurface model here, subsurface, to really understand the role of trees and vegetation for carbon sequestration. Okay. How can trees really help us? And we are trying to look at those things in terms of normal environmental conditions, extreme heat waves, moist extreme heat waves, and when you do a lot of irrigation, a lot of or in ways you're getting a lot of rainfall. So in what environmental conditions are you going to have a lot more CO2, or you will sequester a lot of CO2? So we did this assessment and we found these are the net ecosystem exchange that we'll see. Not generally, we can see a lot of high spatial variability. There's a lot of active CO2 sequestrations in parks, which is followed by vegetation in residential areas. Good news. But as soon as the environmental conditions are different, then this doesn't always hold true. You might be releasing carbon too. So what we have developed is an environmental benefit score where we have divided this area into multiple zones where communities now can use this as the decision-making mechanism and to say, okay, these are the conditions right now. Is it good or not good to water your lawns or irrigate, and what should we do? What are the impacts of CO2 on this? So those were the regional examples. Now let's start looking at some finer scales. So this is a LiDAR data at street block. So this is Google Earth image, I believe. And then here is the cross section that I'm showing over here. And you can see with a 0.5 or 2 feet resolution LiDAR data that we have, we are able to really capture where the light poles are. Okay, that's the resolution we have. We can really look at the tree canopy in the crown and the buildings and heights. So we have made this data open source and available for community to use. And we are using these type of data sets to really use that into a lot of products that we are developing. So this is just a LiDAR cloud point data sets over the downtown area. just showing the heterogeneity and the things that we are able to capture. So how can we use the regional climate models that we have with these data sets to really come up with physics-informed machine learning algorithms that can go down to scales that communities are interested in? So here is an example of using this data set to come up with temperature deviations, and then that can really help communities to make decisions. I'll take a deeper dive in a few slides on this. So the approach we are taking is called urban informatics, where we are using a lot of observations that luckily we have. This is the previous observation through an NSF-funded project called Area of Things, which has transitioned into SAGE NSF-funded project. And we have parcel level land use data set through CMAP. We have LiDAR morphology data that I just showed you, the climate model expertise that we have, and machine learning algorithms. And if you massage all of this, right, what can you create? We have traditionally only worked with the data sets that we are comfortable with, like standard observations that we know, and we just take those 5 stations and start calibrating the model and publishing at that scale. So, but how can we use these parcel level land use data that the city has? A lot of observations which are not yet used, which are low cost sensors to bring all these data sets into one framework. And we produce these state level temperatures. Okay, now this is just a zoomed in view of downscale 1 kilometer climate predictions to sub-meter scales at the street scales. And that can really help planning. For example, if you overlay this on Google Maps, you can identify and think about, okay, where to plant trees. There's no point planting trees here. The temperatures are not that high in comparison to this area average, but it would really be advantageous to plant trees here or wherever it's possible. So city of Chicago, I don't know, how much is it? $45 million, some $1 million, don't quote me, investment that they have committed. The previous administration till last year planted around 19,000 trees over the last 2 years. They would be planting 45,000 trees. The plan is to plant 45,000 trees. And these kind of results can really help cities make informed decisions where to really strategically plant trees so that they can have an impact. Where, of course, they will be helping this region, but also when they plant here, of course, it will help the neighborhood as well. So this is the data I was talking about. We call it Height Tab Chicago, height map of trees and buildings for the city of Chicago. So this really, the cross section that I showed you, we have created this open source data set. This is available. If you want to play with that, please feel free. But what we have found is from this analysis is, for example, a lot of studies have used this NLCD data set, but from 2017 for Chicago, and have been used in policy and research. But based on our analysis, we found, okay, this is not the true representation of the tree canopy, but this paper is under review. Hopefully reviewers will accept that what we are trying to say makes more sense. So, and we'll start using the much more refined data sets for tree canopies and building heights. So now the question comes, how can we help communities? So to help communities, we need integrated urban sustainability solutions, which are multidisciplinary and should involve multi-stakeholders really to do actionable research. And this is the fundamental premises of all the IFLs. So let's imagine a situation where we go to a mayor's office and say, okay, we have a social scientist who comes up with a heat vulnerability map, right, on the person's table. Utility gives an air conditioning consumptions within a city, and then a climate scientist like myself presents a roof surface temperatures, and then that mayor has $10 million to invest, and he wants to invest. So all 3 maps are showing different stress points. So how do you make a decision to really look at integrated approaches? What we are saying is, you don't have to do rocket science here. You need to really do a very simple analysis, right? So we created changes in temperatures with green roof from the previous simulations, for example. And then you just plot them on a scatter plot with these dots representing different census tracts on the reductions in roof surface temperatures and heat vulnerability index. And then give them a, say, 50th percentile cutoff on the both sides, and these are our census tracts of interest. Once you do that, you have narrowed down your problem statement that, okay, I don't have to worry about all the census tracts. These are the interesting census tracts that I have. And then you overlay that with, I believe this is air conditioning consumptions. And then again, give it a 50% cutoff, then you have much more smaller problem. So we need very simple solutions. That's what I was talking about, to really come up with investment strategies. And of course, if you go and pick any census block, it's huge by itself too. But we are scaling it down the problem, and at that scale you can use NVMet, you can use machine learning approaches that we have, you can use community input, and so on, multiple ways to really narrow it down. But we need to really come up with ways of narrowing down the problems. Okay. I think I showed this, right? Yeah. Okay. So now question comes about environmental justice. Okay, this is mapped by Illinois, Northeast Illinois Climate and Environmental Justice. They created a dashboard that really shows overburdened and underserved disadvantaged communities. And if you look at from environmental grids perspective, you have temperature, humidity, PM and ozone and so on, and impacts of climate change to really look at enhanced environmental stresses. While from a social sciences lens, the metrics are different, which are demographic information, population growth, and population-based persistent inequities. How do you massage both of them to really understand the environmental justice? Okay, these are the maps which are showing how Chicago has become a lot more polarized over the last 4 decades. It was really okay distribution with respect to income, but it has become a lot more polarized. These are the emerging hotspots, air quality, and heat vulnerability that we produced. It is 8th in income inequalities. When I created these figures a few years back. And also, if you look at inequity and inequality, this is a good term. If everyone in this room gets the same salary, like, we're not motivated to do anything. We're happy. Which there should be an inequity, but what's the healthy level of inequity so that there is some motivation to do things? So that's where the question is, and how can we really address these kind of issues? Not to have that much disparity, but some healthy level as well. So these are the questions we are trying to address. If you look at crimes in cities, you might have seen a lot of TV shows in Chicago looking at crimes. This is the total spatial distribution of Chicago over the first 20 years of the century. And you can see these kind of maps look similar to income disparities as well as heat vulnerability. And we use this map just to extract the data clocks. And you can see over the summertime, there was a lot of crime, especially in the early 2000s. Then the crime started decreasing. And it's due to a lot of efforts that are there because of the way regulations and rules are and policies are made with respect to policing and that kind of effort from social sciences lens, but also a lot of efforts that the previous administrations do to increase sustainability and resiliency in this region. If you look at the weekly distribution, just looking at the data, no, we haven't done any rocket science in this. These are the hours of the day, 24 hours, and these are the days in a week. Okay. And as you can see, during the daytime, and especially during the evening hours when the temperatures have been relatively hot, that is the time you can see a lot of crime happening. Okay. In the morning hours, there's no crime. This might be a completely different figure if you're in Vegas. Okay. The crime happens during the nighttime there. Okay. So we are trying to have a signal from this that what's the crime distribution. I'm not sure if I have added I have not added a slide where we are looking at these distributions with temperature as well. And we are seeing the signs with respect to seasonality, as well as early occurrence of summer. For example, in March, whenever the temperatures go really high for a few days, we see spiking crime rates as well. And different types of crime, like burglary or assault or type 1, type 2 that PI has that categories. So we are seeing those kind of distribution. The question is, we are trying to address the causal relationship now, which we have not yet. So we are just doing data analysis, but how do we scale this to really identify the causal relationship is our next step. So all the information that I shared, we are creating visualization tools to really help policymakers, scientists like us, developers and community members to improve decision making. And we are meeting with the communities, getting their feedback, doing an iterative learning where communities feel that this is their product. This is not our product. They should feel that they own it. A sense of ownership is important when we are engaging with communities. So we call this eJust. This is a NASA-funded project where we are looking at environmental justice using urban scalable toolkit. The toolkit, our vision is there are multiple toolkits. You can do it in ArcGIS and make up a toolkit, right? Put different data layers and that's it. We want to make something that is flexible, that is extensible, reproducible, reportable, scalable, and accessible. So how do we bring in all these flavors in a toolkit so that it doesn't die when the project dies, but the people use it. So I'm going to give a flavor of it. So if you look at the traditional ways, if you're not just using ArcGIS to create a tool, you have to write long lines of codes. What we are trying to say is how do we do these signs in a new way where you can have a shorter code to work with. And this is the kind of architecture we are working in with. We are having a front end and a back end. We are creating everything from the scratch with the prior knowledge that we have to really create a framework that can be used operationally. Okay, which will have a lot of interfaces. So you have the modeling and data management and the science tools on one side, while we host it on our website with a server that is sitting next to it, and then high performance computing is at the background. So that's our goal. We want to make sure that we can handle data from different sources, say satellite models or observations. At the same time, it should be both science facing as well as public facing. So when you go in, it will ask you if you're a scientist or you're a community member, then it should give you an interface that that person should be comfortable with. And if you start toggling things, you're going to open up the whole gamut of the tools. So our toolkit has spatial exploration capability, temporal overview, as well as doing data analytics. And is this a video? Oh, no. So this is just kind of a few pictures and snippets and videos of how the toolkit look like. We also have the ability to really plot two things side by side so that you can compare and have a visual understanding of how it matters and what it matters. We have created a slider as well so that you can overlay on top of each other. And I'm going to give you a demo of how it looks like just for half a minute. So you are going to say, for example, use WOW forecasts. Okay, you can use observations and you can run it. This is offline version. You can, as the data comes in, it will show the forecast and you can see where the temperatures are and how does it look like. You can go and click at any point and you can see the time series of that. And if you click multiple points, how does my neighborhood compare with respect to others? You can see that type of interaction as well. As you activate the social demographic layers, you can see how the correlations and the relationship between those with respect to temperatures. We are working on temperature right now, but we include air quality and other variables. So it's easy to include others if the prototype is right. And you can look at different racial inequities that are present in the neighborhood and so on. So it's doing a few other things. Let me just go forward. Yeah, it's kind of creating two plots side by side to really showcase a few comparisons. So this is satellite-based product, and here is the social vulnerability index that we have created. So if you want to see how satellite products compare with the vulnerability index, you can see those kind of things. So and then as a user, you can all these things would be clickable and selectable. So as a user, the way, for example, you see EJ screen, you have multiple things to do. So this will have a similar ability as well. But it will be a forecasting tool where you could see these things over the last 3 days and what it shows over the next 3 days as well. And our goal is in the future, we want to do data assimilation with the crocus that we have, satellite data, so that we can improve our forecasts of hydrometeorology and also flooding. So one more application here. So here we are trying to also combine the temperature data sets that we showed at 1 kilometer resolution previously, and also the street scale kind of a modeling framework that we have. Since we want to do operationally, we are not going at street scale. This is just an example at using machine learning algorithms at 250 meter resolutions. And you can really help communities make those decisions. When we showed that animation over Chicago, it looked cool, but I think something like this would be really helpful for stakeholders to make decisions where their assets are. And this is just an example with heat. And we can do something similar for flooding too, which is underwater. Other examples are related to shading. So I'll just zoom in here. So you activate these things, and we are just showing dynamically how do we do that. But you can put the buildings and then activate, and then here I think it's around 2 p.m. we are showing the shades, where the shades would be, so that it can really help you with urban planning questions and putting trees as well. So you can look at these questions from different lenses. So the applications of these are in multiple areas in respect to environmental justice. You bring all these layers together, and then that really can help improve decision making. So if you think about urban science, it's not just about modeling urban environments. It's all about complexities that are related to societal and infrastructural issues. And we need to address them in integrated fashion. I'm going to give you a few examples that we are working with. This is a project with ComEd, where we are looking at afforestation scenarios for the utility, where they could really put trees to really help make them resilient with climate change, as well as to really help communities where they serve. So if they have densely vegetation, if they have tall trees which are taller than the buildings, or if they have transmission lines and power lines, they should have shrubs. So how do we incorporate these kind of things with climate change and also with changing populations? These are EPA approximations of changing projections up to 2030. So how do we use all of this to really make decisions? So this is just a data analysis looking at electricity and temperatures. If the temperatures are too low and too high, how does electricity consumption change? And this is the sweet spot where the electricity consumption is minimal. So what we learned is if it's really hot, even a 1 degree increase in temperatures leads to around 0.38 gigawatts of electricity demand. I'll give you a simple example. If you keep your air conditioning at home around 74 in summer, it will kick in maybe maximum 3 hours or within 24 hours. If you try to keep it at 72, maybe 6-7 hours. But if you really want cooler temperatures and put it at 68, it will run more than 15 hours a day. So that's the huge difference that it makes on energy consumption when you just change the temperatures by a very small amount. You could easily use ventilation and those kind of approaches to really decrease your energy consumptions. So if we are looking at future scenarios and then how with business as usual or worst case scenarios, what are the demands that the energy consumption would have? These are kind of histograms of probability of warming. And these peaks really talk about with different scenarios where the peak is. And the second hotspot that you see in these curves talks about the UHI kind of a hotspot that this region is producing. So we can look at scenarios of afforestation that can mitigate, offset these hotspot form. We have proprietary data with NDA with respect to where the poles are, infrastructure of the utility are. We have the land cover data. We massage all of them together to really understand climate resiliency for that and come up with scenarios developments that can really help utilities and others to come up with solutions. Likewise, this is a second example where we are doing NSF PIRE project, Partnerships for International Research and Education over India, where we are looking at a very holistic picture of addressing issues related to air quality and heat in New Delhi. And this is a snippet which shows about our approach, our coupled infrastructure approach, where everyone is a resource user. You could be an infrastructure provider or a utility or a resident. You can take different roles as an actor when you're trying to achieve these goals. And the question is, how can we decarbonize transportation sector when we're looking at sustainable and resilient cities? There are problems related to traffic congestion, heat waves, and air quality. And how do we solve all these problems in a very integrated fashion? So Delhi is our test bed. We are looking at what can we do today, as well as what can we do at climate scales, because in India, they have an emission targets that we will not try to reduce like the other countries are doing. You have already done your development. We want to have still the development and then we'll slow down. What we are trying to think, okay, you will go with the path that you have, but how about you try to do a little bit so that this curve is a little bit steeper. So this is the PM 2.5 concentrations over Delhi at 400-meter resolutions. So what happens locally is that whenever poor air quality is there for whatever reasons, there is an air quality management system, which is called as graded response action plan, draft policies, where whenever there is a high pollution, government reacts, an alert is issued, and intervention is lifted after 3 days and it's achieved. Okay, but policies are odd even schemes. Okay, all the cars with odd license plates will drive today, others tomorrow. Let's close the shop, odd number of shops today, and the next others will open tomorrow. So those kind of interventions happen. What we are saying is, how can you come up with air quality measurements in electric vehicles and transportation use patterns and user behavior changes, so then you can be proactive rather than reactive in these strategies. We are combining our urban climate expertise in transportation and human systems with colleagues Also, education is quite important as we want to change the human behavior. How do we do everything together to really address transportation air quality coupled infrastructure systems to mitigate these issues? The second is the Clean Energy and Equitable Transportation Solutions Fleets. This is an NSF UKRI global center that we started last year, where again we are focusing on transportation over the Great Lakes region in the US and also South Wales and West Midlands in the UK. And how do we address issues globally with two test beds so that we can learn from each other? We are talking about clean and equitable transportation. This is more like user behavior, emission inventories, and travel demand management. This is hard infrastructure, which is related to transportation sector, hydrogen-based economy, and regional circular economy. And this is where we sit in with respect to climate change. Okay, how are the impacts of those things on climate change? We have a cross-cutting goals related to decision support, something similar that I showed previously. Public health, economic pathways, looking at cybersecurity, which is quite important when we look at urban systems with smart and connected vehicles moving on, and also impact pathways in terms of governance and policy. And these are all our partners from United States. We have University of Illinois Urbana-Champaign, UIC, and DPI, we lead it. And from UK, we have Birmingham and Cardiff as partners. These are our global partners here right now with the partnerships that we have. And we are bringing this project in other countries as well. You all are familiar with the DOE Urban Integrated Field Laboratory. We are part of CROCUS. CROCUS stands for Community Research on Climate and Urban Science, led by Oregon with 12 academic and 4 community partners, 60 county-wide region with around Chicago in 3 states. And results are specific to the region, but we're trying to work on methodologies that can be used everywhere. We want results to be, the methods to be portable and scalable. Okay, so finally, this is my last slide. So the takeaway is, how do we make cities and communities resilient? We try to address these kind of questions and try to also relate that we really need fundamental applied translational and collaborative research working across the domains with stakeholders, with industry, with nonprofits and communities. And climate change impacts are disproportionate in cities, that we all know. I learned a lot today from you all, what happens in Baltimore. And then we need to really bridge scale gaps. It could be vertical scales or horizontal scales, right? Across region, local, and hyperlocal areas. And also we need to design tools for specific science questions and research needs. So one tool can't fit for everything. You design you ask a question, and based on the question, you design methods and tools to achieve that. And one solutions can't fit all. You can't think of, okay, we have identified that tree planting is the path to go, and let's keep planting a lot of trees. It's good, but it won't solve the problem. We need a mix of solutions. And then at the last, we need multidisciplinary and multi-stakeholder engagements if you want to really achieve actionable science and cost-effective solutions. With this, I'll close my talk. Thank you very much.
Thank you, Shiv. So maybe if I could ask you, can you escape from the full screen mode? That way we'll be able to see if people are coming in on the chat, because you're on Zoom there, right? Oh, wait. Whose screen is it? It's my screen. I don't know what I'm doing. How about you have a question?
Yeah, so since you talked about like urban informatics and such, I was wondering, when you have these data sets, like especially like the 2-foot, I think you said resolution LiDAR data, that's, I guess I'm generally in favor of open data and everything, but something like that, how do you consider the, I guess, privacy or surveillance implications of publishing?
This was already a public data set available. So what we did is we tried to use that data set to make these products. So and also a lot of data set is published by the city of Chicago in the data portal, and also Cook County data portal and all. So what I'm trying to say, there's a lot of public data available already, but we don't go outside our silos to make sure that how can we use those data sets to really inform our science. So this is just an example, and luckily we had from morphology lens that data sets. But there are a lot of commercial data sets, for example, I talked about in the morning, like Planet and other satellites, other companies that are producing. And how do we use that kind of data sets? And I think we need to find pathways in which we go outside of our traditional bounds of doing science and see what's the state of the art available or what's available in the junk that we never go and look. And how can we use that to really put together something? Yeah. So the data set was publicly available already. We used that and cleaned it up. Yeah, we didn't create the data set. We cleaned it up and make sure that it's usable by us.
Yeah, do I go first?
I don't know.
Yeah, I'll go first. I guess my question stemmed from your LiDAR urban energy slide, but you've since showed different data products. But I guess specific to that slide, you mentioned that you provide all of your products to the community. And I guess I'm curious how you define community and like examples that you have of how the community has applied your products or has applied these products.
So within Crocus, we have 3 community organizations. At the same time, we also work with we share these results with the city of Chicago. We work a lot with Chicago, Metropolitan Mayor's Caucus, which represents 275 municipalities and the governance. And last week I gave a talk to the Housing Environment Committee of the things that we are doing. So we see these pathways in delivering the science that we are doing. And we co-authored, for example, the Chicago Region Climate Action Plan. So we know the science gaps. We are trying to fill in those science gaps and going to these communities who can be our ambassadors to really tell people on the ground. We hosted town hall, for example, at our place to bring communities there and then share what we are doing. This summer, we'll also host another town hall where the product is a little bit finalized to get their feedback and then improve on that feedback and then make it live so that the communities embrace the feedback that they're giving, because those are the end users that we have, right? The end users need to make sure their feedback is incorporated and so that they can start using. So I think these are different ways in which we are trying to incorporate community inputs. Crocus and here the IFL as well at the same time incorporate in community inputs as well. In Crocus, we have sort of science team meetings. The community partners attend those meetings and participate and provide input in the things that we are doing. This exercise is also helping us to keep us on track. At the same time, communities are also understanding it's not so easy to do the science. So it's the both way. I think understanding is also getting improved and the language is being used where everyone understands everyone's lens. It's not so easy that if you ask a question as a community member, we can come up and say, okay, this is the result, use it. It's not that straightforward. While at the same time, we are also more cognizant of community needs and the things that they want. So I think having a dialogue and understanding is important.
We've got a question at Penn State.
Go ahead.
Great talk, Ashish. A lot of material. I had a question. You showed a high resolution surface temperature map, almost like in the canyon, the urban canyon. You had the heterogeneity there.
Yeah.
How much do you trust that variability that you've modeled there? And has any of that variability actually been validated by observed measurements?
Yeah, so when we created these hyperlocal temperatures maps, we published them in GEMS. What is it? What's the name? Advances in Earth Sciences Modeling journal. So I think those results are published. So I can send you the link for the paper where we really we found the heterogeneity within the urban systems and published those.
So is it the AOT that you're using to validate?
Yes, using the AOT data sets. So we have published those results.
Okay, thank you.
Grace, you had a question?
Questions. One, I was just, you said it offhandedly, but the fact that when it's a little warm for a few days in March, that crime increases.
Yeah.
I know you said you haven't analyzed the causality yet,
No, we have not. We want to analyze the causality.
but do you have like any inkling of what it could be? Is it just that like burglars like nice weather as well? Like,
So that's an open-ended question, as I said. We just looked at the relationship. And what we are also seeing that is it's not just that it is hot today that there'll be crime. It's the continuous hot weather compounded event that is causing that outcome. That's hypothesis.
okay,
We need funding to validate that.
I see.
But this is just based on 2 data sets looking at it. So if it is hot, persistently hot, you can get it. And the way of compounded events is it is hot for 2 days, it's not that average temperatures, hot again, average temperatures, hot again, that might lead to it. So it's not that just today is hot and today I'm going to get mad and I'm going to do something.
Yeah.
So it's the compounded events, that's the hypothesis which would result in that. That's why we're also seeing the signs that these things are not happening in the morning hours or early hours, but also during the late hours when your aggression level, and this is again hypothesis, where your aggression level has increased, could have increased, have temperature might have some dependence on that, and that is the reason that it's happening.
Okay.
Yeah.
Wow, really cool.
So again, all hypotheses.
Yes. And then my second question was, throughout your talk, you discussed a lot how you want this to be like actionable for the community. So I was wondering if you ever take your results to like policymakers or stakeholders that then, turn your results into action.
That's a good question. So I would say no one has said that we have used your results yet.
Okay.
Okay, but they listen to our results and invite to those meetings to hear our perspective. Maybe they have never shared that, but they might have used it in their decision making,
Mm,
but no one has explicitly said that to us.
Okay. Thank you.
I'm aware we're at the hour, but are there anyone waiting to ask questions there in the room at Penn State?
I have a question.
Go ahead.
You have talked about the community engagement thing. So when do you collect the community feedback? What's the process? Like, what are the questions you ask or how you document their feedbacks and then further use it for this study?
So I'll share a different, I have the share right?
Yeah.
So through Caucus, for example, we have community engagement lead, and those people really talk about how do we then engage with the communities and get their feedback from them. But from my own perspective, we also have Center for Urban and Rural Environmental Sustainability at EPI that we host. And if you look at, for example, any year project and look at our engagement process here, you see the screen. This is our engaged process, right? We collect community needs and priorities, what they're interested in, identify candidate projects, and do those projects. So this is the one kind of approach that we use for community engagement. But different projects have different demands, and based on those demands, we develop different engagement strategies. And I could just show one because I thought of it.
Okay, thank you. And another question is, there are several actionable items. So is it mainly for neighborhood scale or city scale, or how does it differ? Like, what's your perspective on that?
Well, it depends who's asking the question, right? If I'm a resident, I would say what happens to my basement flooding. I don't care about others, but just make sure it's resolved. But if senator is asking a question, then they are looking at much broader scope. A municipality mayor is looking at a different scale. An alderman is looking at a different scale. So it depends who's asking the question and what kind of outputs or results we have to share with them to really help them with that question. So it's a difficult question to answer, but it depends on who is asking and how can we support those questions. And yeah.
Okay, thank you so much.
My question was centered around, you talked about scale a lot within your talk, Ashish. And I just wanted to know, with combining different resolutions from a spatial standpoint, does that ever impact greatly what variables you're seeing contributing to the urban system?
We have combined, so for example, when we did multi-scale modeling, we used the global climate model output, ran WRF at really high resolution, feed that back into NVMet model to comment on what happens at the neighborhood scale. So we did that as thinking as a multi-scale modeling. But in other instances, we have just looked directly at using machine learning at neighborhood scale. So I think the inferences, I don't know how to, I might have forgotten your question. It depends on the question you have and how best you can answer the question. Is it through going through the different spatial scales, or maybe directly working at those scales? And what expertise do you have to achieve that? That might also play a role in answering, in defining the scales, right? And also, how much computing power do you have to do that? At the same time, how much money do you have to do that? I think it boils down to these complex questions, which are not just science questions, but also personnel, financial support, time frame you're interested in answering the question, and so on. So I think it's a very complex answer to make. If you give me hundreds of millions of dollars, we'll say, okay, we'll put it on HPC, do this and that, and then create a new model that will do it. If you give me $10,000, I'll say, okay, I'll do some statistical downscaling and tell you what happens here. So I think the question and the answer depends on multiple reasons, multiple aspects.
Thank you.
That helped.
Yeah, I think we're out of questions here at Penn State.
And we're out of time. So thanks again, Ashish. Great job. And, all right. Well, and I think that's the semester, right? So thanks everyone for a great semester. And I'm sure there's gonna be lots of follow on across the IFL and across the campuses in response to what we heard this semester. So take care, everybody.
Thank you.